Today we're going to talk about hybridization, how you define a set of axes, optimal arrangements around geometric shapes, orbital characteristics, and then once we've got all that straight, I'll talk about examples. Are you okay?
Yes, Professor.
Optimal geometric arrangements of 2 to 4 objects about a central point and orbitals to point at them. It's too boring. So, how to be happy in multiple romantic relationships. Part 1. 2 partners. Now let's imagine, UN, 2 boys were chasing you at once. They both find you equally attractive, but they find each other repulsive. What's the best way to organize them on a set of axes that will define X, Y, and Z? They will arrange in what geometry?
They will align linearly.
Yeah, so if we put thing 1 and thing 2 on the x-axis, for instance, they'll align all 3 points in a straight line. And what's the dihedral angle between the 2 lines?
180 degrees.
800? Gosh, 180 degrees, right. Let's talk about orbital characteristics because we need to know which orbitals to use for 2 objects aligned at 180 degrees. But before we go into that, we need to digress and talk about characteristics of orbitals in general. What are orbitals on atoms called, UN?
Atomic orbitals.
And how many nodes does an s orbital have?
There is no nodes.
How about p, UN?
There is 1 node.
1 node. P orbitals have 1 node. How many would d orbitals have?
2 nodes.
And f orbitals will have?
3 nodes.
3 nodes, yeah. If I combine atomic orbitals in a molecule, what are they called?
Molecular orbitals.
And if I combine 2 atomic orbitals, how many molecular orbitals will I get?
2.
If I combine 3, how many will I get?
3 molecular orbitals.
And what about 4?
4.
What about 105?
There'll be 105 molecular orbitals.
In other words, combination of n atomic orbitals gives n molecular orbitals. Always. You can count on this. Molecular orbitals form from 1s and 1 p orbital. What do you call them, UN?
sp orbitals.
Yeah. If I form orbitals from an s and 2 p's, what do you call them?
sp2 orbitals.
And what do you think I'm going to ask now?
sp3 orbitals.
Yeah, if you combine 1s and 3 p's, you get an sp3. And besides all this, you have to get your geometry right. That's critical. This is a picture of the orbitals we have at our disposal. 1s, and how many p orbitals?
3 p's orbitals.
3 p orbitals. Yeah, 3 p orbitals. You don't have to align them on any particular axis really, but it's convenient to put 1 p orbital on the x-axis. Is the one on the z-axis, UN, perfectly aligned with z?
Yes.
And what about the one on the y-axis?
It is perfectly aligned on the y-axis.
UN, these 2 boys are chasing you along the x-axis. What 2 orbitals can you use to bond with them?
Orbital s and px.
Good. And when you combine 1s and 1 p, you get?
sp orbitals.
Yeah, we get sp orbitals by combining s and p. Thing 1 and thing 2 are sitting there in a straight line, and the atomic orbitals mix this shape for bonding to thing 1, and that shape for bonding to thing 2, and when you superimpose them, you don't see the little lobe underneath. This is always the shape of sp orbitals. It doesn't matter if they're spy or spz or so on. The x is just there because we chose to align on the x-axis. Let's imagine these 3 boys are chasing you in the xz plane. Now remember, to form 3 molecular orbitals, we need 3 atomic orbitals. Which 3 will we choose to give us a bonding arrangement in the XZ plane? Can we use the S?
Yes, we can.
Can we use the PX?
Yes, we can use the PX.
Can we use the PY?
No, we cannot use the PY.
Can we use the PZ if we're bonding in the XZ plane?
Yes, you can use the PZ orbital.
So which three orbitals will we use to form our sp2 hybrid?
S, PX, and PZ?
That's right, yes. And when we combine them in that plane, we get three even orbitals. Planar, trigonal planar. Only one of the p orbitals, arbitrarily px, can point at one of the things perfectly. The other p orbital, it can't. So the molecule reorganizes the atomic orbitals, mixes them up, and gives us an sp2 hybrid. Now life gets really tricky, because you've got 4 boys chasing you all at once. What you going to do? This is hard. How are you going to arrange 4 points around you? What shape can you sit in the middle of to arrange those 4 things equidistant apart?
Tetrahedron.
Yes, that's right. It's a tetrahedron. You sit right in the middle, and you remember what is the dihedral angle between 1 and 2?
It has a dihedral angle, 109 degrees.
And what will the angle be between 1 and 4?
It will still be the same dihedral angle, 109 degrees.
Can I choose any of those 4 objects and get a different dihedral angle?
No, Professor.
So let's say I put the central point and thing 1 on the PY axis. Besides the S and PY, would either of the other 2 p orbitals be of the right geometry to bind directly to 2, 3, and 4 if we didn't hybridize them?
No.
We have an S and 3 p orbitals. Let's mix them up. When we do that, even though that tetrahedron doesn't fit nicely on our 3 axes, the orbitals that we get after mixing, they point to the corners of the tetrahedron. It's actually very hard to draw superimposed orbitals. The diagram isn't quite right because the s orbital is really on top. Okay, let's look at some examples. How many things on HF, how many bonds and how many lone pairs, Yuan?
1 bond and 3 lone pairs.
We know fluorine brings to the table 7 electrons. It's a halogen. The hydrogen brings 1, and the HF share 1 each in a bond. So that leaves 3 lone pairs on the fluorine. So there's 4 things to place. What shape's it going to be, Yuan?
Tetrahedral.
Yes. And what will be the hybridization state?
sp3 hybridized.
Good. Let's walk along the periodic table to the left. Water. How many things, that means bonds and lone pairs, are on the oxygen?
There are 4 things.
How many bonds?
2 bonds.
How many lone pairs?
2 lone pairs.
4 things means the hybridization state will be
sp3 hybridized.
We walk 1 step to the left, Yuan. The next element is
Nitrogen.
and nitrogen with hydrogens around it. The simplest molecule is.
Ammonia.
How many bonds on the nitrogen, Yuan?
There are 3 bonds.
Are there any electrons left for a lone pair?
Yes, 2 electrons.
1 lone pair. So totally, how many things?
4 things.
And what will the shape be of those things around the central point?
Tetrahedral.
And the hybridization state?
sp3 hybridized.
Yes! 1 lone pair, 3 bonds, sp3 hybridized. We'll put that upstairs too. Now we have methane. How many things around the carbon of methane?
There are 4 things.
So the hybridization state must be?
sp3 hybridized.
And this one, will it be a perfect tetrahedron?
Yes, indeed.
Will the tetrahedral arrangement in ammonia, water, and HF be perfect?
Not really.
That's right, because lone pairs repel each other and bonds more than bonds do. So the shape will be a bit distorted, but the basic shape is tetrahedron. Let's talk a bit about charged things. The ammonium cation. How many lone pairs, Yuan?
There are no lone pairs.
How many bonds?
There are a total 4 bonds.
So what's the shape?
Tetrahedral.
And what's the hybridization state?
Still sp3.
A methyl anion. How many bonds around the methyl anion, Yuan?
3 bonds.
How many electrons are left that are not used in those bonds?
2.
In other words, 1 lone pair. So how many objects totally around the carbon?
There are 4 in total.
And the shape will be?
Tetrahedral.
And the hybridization state?
sp3.
One last one. A methyl carbocation. How many objects are on the C?
3.
No lone pairs?
No lone pairs.
So how will those objects arrange around the carbon? Is it going to be an octahedron?
Nope.
Pentagon?
Nope.
A tetrahedron?
Nope.
What's it going to be?
Trigonal planar.
Yes. And the hybridization state?
sp2 hybridize.
What's left on the carbon? It doesn't have any electrons. Which orbital haven't we used?
1 MTP orbital.
There it is. So that carbocation only has how many electrons around the carbon?
6.
It's hungry for more to make a stable noble gas arrangement. If a nucleophile approaches, which empty orbital will it use to bind to?
An MTP orbital.
And when the nucleophile binds, will the hybridization state of the carbon change?
Yes.
It will become?
An sp3 hybridize.
With 4 things around it. In a related video, I will explain hybridization states on more complicated organic molecules. Thanks everyone, and goodbye. Thanks for listening. How do you say thank you in Vietnamese?
Come on.
Come on. Is that right?
Come on.
Come on.
Come on.
Come on.
Yeah. Yes, that's right.
Really?
Yeah.
Oh, you're just being nice.